It's so common that it's abbreviated CI. There's a whole software ecosystem around continuous integration. I think it should be used and adopted by systems engineers, but it's not yet. And then a couple of first steps, that is research things that I know about, but haven't actually been personally involved very much about really formalizing, automating this process of formalizing requirements. So I will use actually quite a bit examples to go through to motivate these things. A couple of things that really seriously failed in industry, and failures are always good to learn. You know, why did it fail? How do we avoid failure next time over? So my thesis here is systems engineering and model-based design are two worlds that really need to converge. I think they're on the process. If we look at the systems engineering side, there is modeling and simulation in the V model and how people talk about it. That's completely normal. Lots of the systems engineering tools, vendors, and the simulation ones, they talk about that. And it's quite common. So you have requirements and performance targets. You start with an early system design, subsystem design, component design. And so many industries do this really well, but the tools are not integrated today because there's simulation tools and there's systems engineering tools. They don't even know the shortcuts for the standards, vice versa. I mean, the one exception is maybe FMI that the systems engineering is starting to get into. So in each step of these, you have like a smaller V model in which you define your top-level requirements on that level of the system. You systematically build up a solution space of potential solution. You use modeling and simulation to explore these solutions, and then you verify these potential solutions against the requirements. So that is a process that is done. But if we look at the supporting tools, you still have two completely separate silos, the simulation tools and the systems engineering tools. They don't talk to one another. So in terms of the building blocks of standards that I will talk about, Modelica is an open standards system simulation language. Just a quick reach of hands again. Who knows what Modelica is? And more than just heard about it. Okay. Who knows what FMI is? More than just heard about it. Okay, most. So I'll keep this short. It's an object-oriented modeling language, non-causal and equation-based. You model in first principles. You really write equations, and then the equations are transformed into a form that is efficient to simulate and can be actually different types of formalisms. You can solve transient problems, steady-state problems. You can solve particular optimization problems that can be formulated as an NLP, nonlinear program. And on the research level, we are working with and want to extend Modelica to even use mixed integer optimization problems. I mean, the language would allow that, but nobody up to today has really built a backend to do that. And really supports multi-domain modeling, and it's really an open standard that actually works. And I mean, I can really talk about that. We have products that work on different tools giving identical results. So Modelica is actually a very strong standard, much, much stronger than Sysml. It's almost impossible to get Sysml from one tool into the other. People build a whole infrastructure of translation tools and intermediate representations to be able to transfer most of the semantic content of a Sysml model from one tool to the other. At Modelica, we are at a totally different level. We get identical results in different tools. And that's our quality assurance requirement. So it's a much stronger standard than Sysml. So FMI is really, it's an API and its semantics for transient simulation models. It's an XML schema that describes the model structure and capabilities, and inside the zip file there's also a DLL or some executable model or source code. Even there's a source code variant of FMI that describes the model and lets you work with it. So And FMI has really been a big success story because it's supported by more than 100 tools in 10 different categories. And that's really the only standard that is supported somewhat across systems engineering and simulation tools. From these 100 tools, there's maybe 97 is simulation tools and 3 are systems engineering tools, but still, those are important ones. It's supported by Rational Rhapsody to some extent. It could be much better and further. It's supported by No Magic, Magic Draw, and their simulation engines, and some other ones that I forgot now. But at least this is the only, at the moment, that is the only level of overlap between systems engineering and simulation tools, and in order to be able to streamline the process. And so I will bring one example that uses FMI, obviously. Actually, the ANSYS tools, the SCADE suite, they also support FMI, and they also allow, they are also fairly good at some formal things about dealing with requirements. So that's the overlap. There's a third standard that I will skip about. It's one that I think that is quite common on the systems engineering side, but has been seen zero adoption so far on the simulation side, called OSLC, Open Services for Lifecycle Collaboration. It's also had a rocky history. It was a standard that was developed by IBM or pushed by IBM. Then IBM lost interest in it and basically dropped it. And now small companies and others picked up, and IBM still does a little bit. So it's not. It actually looks like reviving. There's a first big OSLC-focused conference in Stockholm in November this year. So it's moving again, actually. I won't talk much about it. OSLC is really trying to reuse existing web standards for tool integration between different systems engineering tools. And it allows you really to have data for one system in different tools and sort of federate the data. So you don't have a very tight tool integration, but you allow to get a common view, fetching data from different tools through this standard and integrating it. So we have built a prototype which is completely open source. If you Google that, you'll find it. This was actually developed by Modelon, an OSLC to FMI connector. So how you can get all the metadata about a model from an FMU into any systems engineering system that understands OSLC. And I think it's used inside one company that I know about, but it's very little used so far. So, this is all prototype level. Also some more interesting stuff about connecting formal methods to natural language later on is prototype level stuff. It's not, you can't buy a tool and actually use that today, which is why I think there's a lot of gaps that this institute hopefully can help to close. So real world example. We have a lot of automotive customers, and this example is about fuel economy is won or lost at the system level. You can translate this one-to-one for electric cars and say range is won or lost at the system level. Yeah, range is the magic equivalent on the electrical car level. It's really doesn't quite matter. I can actually tell you another number that is unofficial that I know from a premier European manufacturer that is very good in getting very good fuel economy in spite of very sporty cars. They get out of one of the improvement in fuel economy from one generation to the next, they gain 50% out of improving the engine and 50% out of improving the system integration. Each iteration they do. So you think that it's only the engine. It's not at all. And that 50% does not take into account aerodynamics or something like that. That is only how to deal with energy management and the rest of the car. Yeah? It's not. So you wouldn't think that, right? You would normally say fuel economy, that's the engine. You need to build a better engine. That's not true. It's 50% is from system integration. So, so the example that I'll talk about, is about grill shutter control. A grill shutter allows you to close off the air intake at the front of the vehicle for the cooling, and then with less airflow going through the vehicle, where it has a high resistance, and instead going around the vehicle, you get better aerodynamics and you get better fuel economy. But obviously these things are expensive. Normally that's just a passive dead part, and you would need to control these things. You need them open when you need a lot of airflow. You need them closed at high speed when you gain most in terms of fuel economy. So what you need to do that as a model-based design, you need a model of the hardware that's in Modelica. You need controller software development platform. In this example, I took Skate. I did the same talk with IBM people and used Rhapsody. You can choose whatever you want on the systems tool. I thought I had a little bit more. So the target, this is not the real vehicle. Target is some company wanted the best-in-class fuel economy and thought grill shutters will get us there. And you need active grill shutters that open and close depending on conditions. Fine. So they reduce the drag and improve fuel economy. What's the standard approach with not model-based design engineering? You build the car. Yeah, you develop a prototype of the car, of the active grill shutters. You track test the prototype. And then they realize that the track test vehicle starts overheating. The grill shutter control didn't work. So actually what happened was that they made the car a lot more expensive and less fuel economic. It really totally failed. And then they asked us to figure out why. What happened? Why did this go wrong? They needed new control strategies. They needed better integration. They didn't have that integration in their tool chain. They optimized the subsystem, but they didn't optimize the overall system. So what they had was that the grill shutters closed too much, but they needed more air, so the fans blew as hard as they could, and then the fans were drawing electricity, sabotaging the fuel economy gain. Yeah, so grill shutters were closed, fans were blowing full steam, wrong controls, and boom. Yeah, higher cost, missed targets, everything wrong. One of the reasons there was that they did not really look at the thermal part of this whole equation. You can look at the details of energy management in a vehicle at different levels. The highest level, you disregard the temperatures and simply say, look, all the temperature control loops are doing what they need to do and supposed to do and will regulate the right temperatures. We don't care about that. We only look at electricity and fuel. And we forget about temperatures. And that tool chain didn't have, and so that's how it failed. So how would you do that with model-based design? Well, you build a model, of course, including the temperatures this time, and you define the requirements of what you really need. And the most important one is better fuel economy. You develop a model, develop test cases, and then you define requirement monitors. You need to check whether your requirements are fulfilled at every design iteration, right? When you do your initial grill shutter design, you need to check that you don't overheat. Yeah, and that these interactions are actually taken care of. And so you need to find the requirements violation before you build the first prototype and catch the overheating issue before you invested into building a prototype vehicle. I don't know what they cost, but they cost, 7 digits per vehicle, prototype vehicle, easily. Yeah, millions. And then you improve the system design and check these things out before you commit to hardware. Fine. So now in more detail.
I have a question.
Yeah?
They missed the requirement to begin with. So how is the MBSE approach helping?
Well, they did have the requirements. The process really didn't combine the thermal requirements. I mean, their models weren't good enough. There's thermal models were really separated from this fuel economy model. So that was, it's basically, automotive industry is actually fairly advanced compared to other industries in model-based design. They simulate a lot. That particular company didn't have good integration on that side. There can be a separation between the powertrain people. Big car companies are extremely siloed. So the fuel economy is with the powertrain department. Yeah, they look at the engine, the gearboxes, and all these kinds of things. And the thermal management is, a little bit separated. Maybe the people for climate control are their own little niche group, and some other people that design the temperature loops. And if they are not integrated in that company, there's no information flow. It doesn't work. A lot of that is also just about traditional systems engineering, Had they thought about temperatures when they set up the grill shutter thing, it might not have happened, as an option. There's both things, but it's, I would say, there's many potential points of failure. The models can be not good enough, the tools were not good enough. So the powertrain department that did all the grill shutter stuff, their models didn't take into account temperatures. Some other place in the company, they were looking at all the temperature control loops, but these didn't talk. That's a systems engineering failure, right? I would say, yeah. Not the right people, not the right group of people at the same table. And in companies, there can often just be that one department boss doesn't like the other one, so they don't talk. And then you have the failure coming up. And one level above, they don't monitor enough. So,
question. I want to follow up on your point where you said 50% of the gains are in terms of integration. So by integration, what you mean is that the teams that are designing each of these components, they weren't aware of the things before. It just wasn't that they were not capable of optimizing their system further, but just by taking into account all the other components, with minor changes they could get this better fuel economy. Or is there engineering involved after integration as well?
I'm not quite sure. I get the question 100%. I mean, basically, the issue is often that you do subsystem optimization instead of system optimization. And the typical examples for cars where you can gain on the integration is that you have a lot of auxiliary systems currently driven mechanically by the engine. Your starter motor is driven by the engine mechanically. Your pumps are driven mechanically by the engine. When you move to electrical, you have a lot more degrees of freedom. Suddenly, you don't have a hard coupling between the engine RPM and the auxiliary system RPM, for example. That's where there was a lot of gain. Suddenly, yeah, all these kinds of things. But once you do that, before you did that, the engine people never needed to talk to the electrical systems people, how big is the battery and all these kinds of things. Now they need to talk to them because, the systems get integrated more. And this is exactly the same example. This is a different instance of the same issue. So, because I'm more interested in the methodical stuff, I will go through this very quickly. This is building a vehicle thermal management model with our libraries. You need to look at lots of things, really, to look at the whole system. You need the vehicle model with loads and losses. From friction in the tires to everything. You need the vehicle heat loads. You really need to understand where cooling needs to happen. You need a simplified engine thermal model. You need the coolants and oil circuits with everything. You need drive cycles to understand really. The drive cycles are the way you test vehicles, and they are very different. There's a New York City cycle, which is very different from a highway cycle, which is very different from European test cycles. Now, there's been a little bit more standardization. Japan has cycles. You need different tests for super hot climate. So, for vehicles in Arizona, you need to test for different things than for vehicles in Alaska, etc. this is basically managed by these drive cycles, which try to capture driver behavior in some standardized way, which has its pros and cons. But so car manufacturers, they use 15 drive cycles, different drive cycles in parallel, and they try to optimize that all of them. You try to kind of weigh them in different ways depending on where your customers are. Sometimes you may have to decide for a different model in a different climate. I do know that luxury cars have different air conditioning systems in hot and humid parts of the world compared to cold parts. You need to decide whether or not to have two different models for these types of different conditions, and where to do that, and where it's economic and where it's not. Yeah, you need to look at airflow effects. So maybe you even need to integrate with CFD. And you need the key vehicle and thermal controls. And vehicle controls is actually pretty difficult. I mean, if you look at the complexity level of controls for energy management, it's amazing. And you would need to integrate quite a bit of, to simply understand temperatures in the vehicle evolving, you, for example, need the shift controls. And with 8 or 9 speed automatic gearboxes these days, the shift controls are super complex, actually. So we have standard model libraries for this, where we use the vehicle dynamics library for the whole vehicle perspective, liquid cooling library for the liquids and fluids, and heat exchanger library for details of the heat exchanger design, and engine dynamics for the engine. But let's skip over. It's a fairly complex. Actually, the model is not super complex. Every subsystem you still want to capture as simple as possible. These we try to not have the most complex models, but really the adequate model, because otherwise your design iterations are going too slow. If your simulation always uses CFD and takes 48 hours to complete for a drive, people don't do CFD on drive cycles. You can't. It takes too long. It's not useful for design iterations. So you need to find the right level of model. And so we have basically hierarchical models where we can zoom into the aspect that you need at a time. So on the vehicle dynamics level, we don't need anything of the 3D movement. So in the vehicle dynamics library, we have simplified levels with 1D dynamics for the motion, which are good enough. And in the same library, we have highly detailed 3D models, which you could put into a motion simulator. But you wouldn't use them for thermal management. That doesn't make sense. You need drivers and drive cycles. So we have basically a way where we actually model the human driver in the car that follows, the input from the drive cycle in some way, and the vehicle, the physics of the vehicle, they might or might not allow you to follow the drive cycle precisely, but that's all in standards on how close you need to follow. Typical results, they look like quite bad. So here, this is the speed of the vehicle, this is the engine speed. So those are actually fairly complex test conditions to verify whether or not systems work. Here's typical results. Here we have a boundary temperature, and we can see that this is violated here. But this temperature, this 97-degree temperature, you're allowed to violate it for up to 3 seconds or 5 seconds or something like that, right? So this is still okay in that sense. So the fan speed is low when the vehicle is fast, because you use the speed of the vehicle to cool, etc. Thermostat opens as the engine warms up, so the thing behaves roughly as it should. Yeah. So how do you integrate such a model with a requirements design, and how would you want to do that? The requirements, they evolve some way. They are grounded in something that the product design people call the voice of the customer. What does the end user want? Do I want a $2 million hypercar, or do I want a car that absolutely is for less than 20K and still does what I need to do? and they are really quite informal and imprecise, you know. I mean, some people want a particular sound from their vehicle, and people definitely like a particular smell of a new vehicle, and these things are designed these days. You won't believe it. But from this very informal thing, you can get into something that is very complex. So for complex and maybe safety-critical system, this can evolve into something that in itself is very complex. So if you've ever seen requirements for an aircraft subsystem, you know, they hit you like a brick in the head, because it's a stack of paper this high. It's thousands of requirements, and they better make sense altogether, right? They should be correct, consistent, complete, all of those. And so you have for requirements this problem that they need to evolve from the concept, you know, I need the next generation single-aisle aircraft, you know, the follow-up of the Boeing 737, whatever. And looking at what customers want from such a plane, to, you know, this document that better be correct. And I think there's a lot in that journey that is still quite open on how to do that well, and people and not up to speed with model-based design the way it's done today. So we want some level of semantic integration. In the typical systems engineering community, you say, okay, you try to map the behavior of the system as you want this, the purpose of the system in Sysml. That may or may not be simulatable. You have the requirements on what the system has to do and shall do and definitely shall not do, and then you use simulation to observe these behaviors. And on the requirement side, you have really a huge range from informal to formal. The most informal is really unconstrained natural language. That's where the voice of the customer starts. Then you can have controlled natural language in some sense, more or less controlled. The most useful approach that I know there is really based on ontologies and natural language processing, so that you basically say, look, we have a basic system of rules for systems engineering in general, systems engineering of aircraft, more specifically, like regulations, and then even more specifically, because we've done them a lot, we know air management systems for aircraft, and so we know what kind of rules we need to fulfill. Those rules are put into an ontology, and your language, as you write the requirements, is compared to that ontology, and if it doesn't match or it's not good enough, it's thrown out. And basically, so these tools do that at different levels, but it gives you something which is natural language. You can still understand it just as any English language sentence, but not every sentence would be accepted as a requirement. It will throw out stuff. What you get is higher quality requirements. Yeah? Because it's natural language, but it's not arbitrary language. It is controlled to the vocabulary, and you can control it to different degrees. I will later talk about an example where there is actually a prototype of transforming automatically natural language to linear temporal logic, and prototypes to transform it into Modelica to be able to execute requirements and work with them. Then there is the Sysml, a descriptive programming language. So you generate it on a computer, but it has been designed to be processed and read by humans. Sysml is only partially really executable by computers. And part of it, or it was designed, its purpose was to be for communication between humans. And even though it's a computer language, its design is not necessarily to be analyzed and fully processed by computers. Yeah, the graphics and how it looks. And some tools do have semantics, but they are not so well specified. Not all of it, basically. You know, Sysml has subsets which are fully handleable by computers, and it has parts which are designed to only be interpreted by humans that look at the diagram and interpret the diagram. Yeah, the diagram interpretation is designed to be by humans, not by computers. Then you have executable programming languages like Modelica and a subset of Sysml, again more formal. And then you have fully formal languages allowing formal proofs on system properties like linear temporal logic. And really what I see as an open question is when to use what formality, how to evolve, how do you move from one level to the next, and how to manage this whole process. I think there's plenty of gaps there. Yeah, and you often really need several of these at the same time for the same system. Currently, we are not there, actually, to be honest, to be able to give you a formal proof, anybody a formal proof that this aircraft will never crash, because if we look at model-based design and simulation, whenever we do integration in time, when we have integrators, there's numerical uncertainty, and that is currently not really matchable with formal methods that you can put a formal proof on that this will never happen. You can give it a likelihood, maybe, if you're really good, but not a formal proof. So there's this, when do you want to validate a system to simulation? When would you rather use a formal method as a proof? And which subset can you do here and should you do here? And which subset can you do here and should you do here? And so on. To my mind, completely open. It's even worse because the systems engineers don't talk to the people that do formal languages, mostly. This, given that you teach formal methods here is a difference. But I've not seen that. So I go regularly to systems engineering conference. I haven't seen a single formal methods person there, ever, right? Not met. And so it's not. There's not enough talk there and understanding. And I think that's from both sides. The formal methods people think, I mean, these systems engineers, that's just fluffy stuff. They don't really. I don't think that's true. Because the systems engineers still help to do the definition at the beginning to really frame and define the problem, the overall problem, and you need them. And on the same side, the systems engineering thinks, oh, these formal methods people, my goodness, they can only really deal with this subset. Why should I deal with that? And I think that's really, there's a real miss, Okay, let's go on. Executable requirements and continuous feedback on compliance of requirements. So how can you do requirements verification? We've used a process for simulation-based requirements, just one of the subsets. This is not formal methods yet, right? So you have stakeholder requirements. That's basically the voice of the customer. They are high level, not always testable. That's informal natural language up there. From that, you derive design requirements. They are low level and testable. You would like them to be specified in an open and standard language. In my mind, that doesn't exist. So it would be nice to have a standard that allows you to talk between tools. There is no standard that I know that can encode requirements, including their semantic meaning, to exchange between tools. There's a standard called REC-IF, Requirements Interchange Format, but it only transports syntax. It can transport a sentence from one system into the next, but not what that sentence actually means. It's missing the semantics. The syntax, yes, fine. You can bring a sentence from one system to the other, but not what it means. So these two are typically dealt with in a requirements management system. IBM DOORS, there's several of these. From the point of view of a model-based designer, these are just bookkeeping systems. They have a number for each requirement, and they also have connections between requirements, but only those that people explicitly put in there. They are, high-level bookkeeping systems to make sure that all of the 10,000 requirements for the aircraft are accounted for somewhere. Somebody is responsible, etc. They are needed and necessary. They are not built to support a model-based design process. So we have a real system that we want to build. We build a model of the virtual system. That's what we start with. And then from the design requirements, what we need in order to automate this process and make it really fully computerized is that we need formalized requirements. There's no other way. We need something that's fully computer executable. Sysml is not it, definitely. Then we need test cases, enough if we do a simulation-based requirement. And then we need to bring these things together. So we need to translate the formalized requirements into an executable format, and we would like to monitor these requirements. That's common language also in the research community that deals with this, which does exist, but even though it's small, typically called requirements monitors. So I need to watch automatically for requirements violation. There always needs to go up a red flag. This doesn't work as supposed. And when you combine the two, we call that verifier model. So we have a model and a test case, a model of the real system, a test scenario, and the requirements monitors. And those together will tell us really what things are. So, and then we want automatic batch execution. Because whenever, yes? Oh, I'm sorry. Yeah. So, and then you want this to run automatically. Every time somebody does change something, you want to test them automatically. Then you put all of that into an executable environment. You generate a result report, and that shows a summary of pass-fail results. If all pass, you're done. If not, you need to go back and do the next design iteration, figure out whether your requirements maybe were too ambitious, system will be too expensive, or they had an error, they were inconsistent, they didn't take physics into account. Super easy to write requirements that violate the second law of thermodynamics, because that is nothing that humans could feel, how it works, right? If you build requirements on the first law of thermodynamics, energy balances work out, you can violate the second one. No human has a perfect feel for that. Okay, so you iterate until done. Cool. So, and when things are not met, you can modify on any level. On the result report, you also want to check whether you have complete coverage of all the requirements. Did you actually look at all of them? Not at each design iteration. You want to look at everything. It needs to be efficient also. But you need to check at the end. You need to check all of them, obviously. And that's really what the requirements managers are good at. Are all requirements accounted for? That's a bookkeeping exercise that they are usually okay at. So the question, in order to do that efficiently, is really, what's the degree of automation? How much of that can you automate and really do in quick iterations? Otherwise, who does have the time to work that? So another quick view of doing that: you need the requirements to be formalized and executable. The physical plant, you need a model of that to be executable. That would typically be an FMU. And the executable requirements could also be used in FMU. An FMU, I didn't introduce the term, is a model that complies to this FMI standard. And then it's very easy to couple them. You have a software spec and a software model or prototype, or the real software, depending on what level you are. And then you need the operations. How is that thing being operated? So for aircraft, it's the flight envelope, and for cars, it's the drive cycles, whatever. And you need models of those. And then you want to automate the analysis of all of these and deploy to the team. So you need an exchange of physical models to the software designers, software models to the physical designers, the requirements to everybody, the operations that you need to test against to everybody. Yeah. So there's different teams that work on different parts of these, but all of them you want to have a total system view, not just the subsystem view and the subsystem optimization. On top of that, then you want to develop customized workflows that really allow you to do these design iterations quickly, right? So there's a research implementation available of requirements in Modelica. There's an open source Modelica library based on a 3-valued logic, which says satisfied, undecided, violated. That is based on specific languages for requirements that have existed. Undecided can be because you may have preconditions for testing a requirement which are unfulfilled. So it's basically a question of whether your test actually allows for the right conditions for that particular requirement to be tested. There may be, it's fine to be undecided on the system shall work with both aircraft engines on when you don't need, when that is not the thing that you're currently looking at. But basically, you can only check for those requirements when actually one aircraft engine failed and the system needs to work on basically half the power. What happened there is that people built a quite large library of predefined requirement structures, and they're executable and form a model in the Modelica language that can be compiled, that can be used. They have been used by members of a European project. So there's a nuclear engineering company, there's aircraft companies, there's automotive companies, and all of these actually use a library and are quite happy with it. What I see as missing a little bit and open research is that they haven't been designed and used for sizing and static design, really, the earliest step. They are all for temporal things, do things work over time. When the system is ready, they don't work at a lower level when you size subsystems or components, or they haven't been designed for that. So if you integrate this requirements verification, we have a model, we have a tool for test automation, which is basically reusing and adopting tools from software engineering for model-based design. So if you have a given design task and you have your executable requirements, you want to have, basically, if you put these two things together, you want to have a validated subset of your design task. And you have, we use a software, an open source software called Jenkins, and that's the logo up there for the Jenkins software, for continuous integration that all the time, whenever any change is done to the design, it automatically gets notified and runs all tests again and notifies everybody who gets a fail on their requirements on, wait, here is a failure. And so it's good for teamwork and team integration. If one team member, breaks the requirement of another team member, they will both be notified and see what's going wrong with them. So these trigger on any change, and that is quite useful. We use it, and you do that for every task. But the interesting thing about the continuous integration is that you always check for all the requirements for every single task that you do. So if you design for a thermal issue and you break the fuel economy issue, the different team sees that. You have this. The testing is always on the full system level, while a designer can only work on one issue at a time. And I think that really makes it fairly efficient, because all this testing runs in the background. Nobody needs to do that. So there is a version control system for every file, for everything. The version control system tells the continuous integration system something changed. The continuous integration system tests, and the designers get feedback if anything failed. That's the way it works. Then when the designer is done, then he moves to the next task. And that is actually much more efficient than when you discover these things very late at integration tests. So what this actually is different here is that you test at every single step. You don't have separate phases, and then you have big integration tests where you can have big failures and big loops backwards in the design loop. You get the feedback instantly. Yeah? And that I think is really the difference there. Now, there's often, I mean, this is the idealized way. There's much more often, there are more company structure issues with these than technical structure issues. Yeah.
Organization matters.
Yes, the organization matters. So if the organization makes this kind of working very hard, it won't happen, and you will fail anyway. So there is a match between an organization that is actually capable of doing these highly integrated things, And, these things are possible totally internationally. I mean, we do it for our own software products. We work exactly with the same way, and we have models for testing because we do software for that. And it's no problem to have a completely globally distributed team for that. Actually, it can be an advantage because this process, you can actually do that with the Modelica requirements library and this our test automation in our Optimica toolkit. I won't talk much about tools because that's not what we are here for in academics. It allows you to do this really totally automated. And what you get there is basically a report which tells you at the end, gives you detailed reports, and you see which tests pass and which tests were not tested and which failed for whatever reason. Yeah. For example, you missed temperature requirements or whatever. So we played this through basically in order to show how you can do that with this vehicle thermal management case, where we build a very. So I'm not going into the details. I have previous talks where I look into that, where it's really okay. We have to design the grill shutter controller. And we started with a naive control, just a bang-bang control. Keep them open up to a certain speed, close them down. Realized you can't do that, you still get thermal failures. Okay, we designed then a PI controller, next level up from on-off control, with somewhat tuned gains on opening the grill shutters dependent on the speed of the vehicle. And temperature. You might have a map dependent on speed and temperature, which tells you how open the grill shutters have to be. And basically, really follow through this whole design process. And it went actually really well. We did this only as a demonstration for customers, how the process works. And this was, in that sense, unproductive work. Nobody paid us for that. And even as a small company, we were able to do that because it was actually quite fast if you work in this systematic way. So now I will talk about something that's not really grown on my things, transforming natural language.
So did you use both the high fidelity model and the requirements model, or are they integrated, or was it?
They're integrated. They're integrated on the FMI level. So we did the controller was developed in ANSYS, output as an FMU. The plant model was developed in Modelica, exported FMU, put together, simulated, and the requirements monitors were also done in Modelica. Then the three things are coupled, and then you figure out basically where are your violations and where are things. Important part there is really that you need to couple the software or controls part and the physical part, which typically is different departments and at the right time. But I mean...
So you checked against the requirement using the Modelica model.
Yes.
How computationally intensive is that?
Not very. It needs to be fast. That's actually one thing that I said. And I mean, we definitely don't have a CFD model. If you need CFD data, you do a reduced order model of some sort. Yeah, you might need that actually. So you need basically a tabular model that gives you the drag coefficient as a function of the grill shutter angle, right? You can't do a CFD on that. That doesn't work. If you use a simple model on that level, then you can. So is it detailed or non-detailed? Well, on the thermal side, it needed to be pretty detailed because we can't miss the temperature peaks, right? On lots of other parts, it was not very, so CFD, very reduced. Much faster than real time, if that's good enough, in total execution time.
So the way this works is that you have a drive cycle.
Yes.
You have a Modelica model of some fidelity of the car, and then you map on that the requirements using the library, and you just run the drive cycle and see if you violate the requirements.
Exactly.
Okay.
And then, there could be others. There could be performance measures. So the automotive companies that I know, they run 15 drive cycles, and then they put performance measures and weightings on top of that, because you want better than just... your top-level requirement may be 5% better fuel economy, but you may not achieve 5% better fuel economy in the worst drive cycle driving condition. So, But you can fully automate that still.
And the requirements are mapped as not as constraints, because you want to see that you violate them. So they're mapped as just...
So they will basically lift if any requirement is violated, you get a red flag in your report, basically. But the simulation runs to the end, obviously. It's not like saying over. Because you want to see how much it's violated, under what conditions and why, in order to analyze it. The requirements are basically running along. You could also do the requirements basically as post-processing. You could do that as step after step. And I'm not yet sure what the best process is. Sometimes it may be better to do that as a post-processing step. Because you don't want the requirements...
Could be a combination of performance requirements and constraints.
Yeah.
And you know that either one of those are violated.
Yeah. But the violation, you don't stop the simulation when it's violated. You still want the full results to analyze what went wrong.
And if your requirements existed in doors, can you bring them in Modelica, or you have to write them from scratch?
No, there is no way yet.
Okay.
That is really one of the problems. That is really here. This is closing the gap. And it's a prototype. So I work with a Spanish company called the Reuse Company, which has, on my end, really the currently best tool for working with natural language requirements. They are not well known in the US. They are quite known in Europe. Airbus used them to design the A350 with hundreds of people there. So it's used really in relevant industries. And what they have is really that they work with these ontologies, so that you write natural language, but the language is checked against the ontology. They have a minimum quality requirement for every sentence that you write there, and you can't press return when your requirement is not in accordance with their rule set. Then there is the issue, if you have many requirements, like an A350, it gets into the many thousands of consistency of requirements. You can't check them that like in real time. So they have both a real-time mode, checking against things you can check in real time, and a batch mode where they tell you the next day, wait, that requirement that you wrote there is contradictory to that requirement that your colleague wrote over there in that part of the system. You need to redo.
Does that work? Does that software work across domains, or is it customized specifically by domain?
It's cross-domain, but what you need is basically a new role that doesn't exist in industry. That's a person that can develop, design, and write such an ontology. Yeah, you need people that can develop this ontology, which is, it's not that, ontology is a big word that many people don't understand, but what it really means is you need a domain expert that also understands the value of mapping between his domain knowledge and natural language processing, and being able to code that into this formalism of how to process natural language for requirements. So you need to train a domain specialist that really understands whatever your system is, and then builds an ontology based on that.
Right, but it seems like the usefulness would be dependent upon the domain.
This company, they have all the rules of the systems engineering handbook, the standard one. That's a base ontology that they have in their system. They have a couple of other ones on top. And you could have ones which are, for aerospace, you might want to use exactly the same terms as the FAA regulations for aircraft, yeah? So you know you're FAA compliant. You have the same definitions and these kind of things. So I think they have a couple of ontologies of that already basically in the system. But that doesn't help you if you design next generation, single-aisle aircraft are not yet these more electric ones where you generate a lot of electricity and then you have compressors to get the air in. If you want to do that, that is very specific design knowledge, and that would need to be very specific people designing that. I think I'm running over time.
Yeah, you do. You do.
Yeah, I noticed. So let me do. So I see several ways to verify and validate requirements. You have formal methods. Can check the consistency of a set of logical requirements. You can do simulation. You verify that the requirements are consistent with the physical reality of the system. But there, you cannot do infinitely many tests. You have often, very high dimensional spaces, and you can't test every point in the space. So intelligent testing is really important, and test design. But both of these methods require formalized and executable requirements in different forms. So if you want to, for example, ensure that requirements are consistent in terms of time, you have air OK signal remains low, auto control mode is terminated in 3 seconds. When auto control mode is entered, eventually the cuff will be inflated. That's about the, And if a valid pressure is unavailable in 180 seconds, manual mode should be triggered, etc. So there's a research prototype in these tools by the Reuse company that analyzes natural language requirements, detects temporal elements, formalizes them, and then can assess the temporal quality of them. So how, are they good, are they not good, and can show results in their requirements quality analyzer. And so what they have there is really that they have a natural language requirement, and they do requirements pattern matching. They have a conceptual graph representation inside the system, and then they have a formalized output transformation and bring it into formal representation. That requires really very strict ontologies on the left-hand side. So you have a very controlled language, which is hard to get people to accept. Most people don't like that. It's very typical requirements engineer wouldn't like to be that constrained in how he can express themselves. So there is an issue there about acceptance. So, and if you do that, you can get this formal representation, the internal one, and they can generate, for example, linear temporal logic and can bring it into an LTL analysis tools and LTL results on, is this correct or false? Or they can bring it into modelica representation, and then you can simulate it together with system physics and figure out whether that matches and maps. Where typically the modelica would be compiled into an FMU, and then you can bring it together at that level. That's almost equivalent. So, So you have natural language requirements, use pattern matching to get a graph representation, and then observe. This was just an error. You should have seen that whole picture. And then you do a formal transformation. So I will skip about this, but so that is natural language, and it's translated into into a linear temporal logic, and that that temporal logic then can be analyzed, and you can figure out whether there are contradictions in terms and stuff like that. So now this would all be really pretty nice, but this is seriously prototype level. I mean, you can talk to these guys. The guy that's the CTO is also a professor at the University of Madrid and doing research. So they're probably a good guy to invite if he finds time. Yeah, and then, so how to do a shared resource arbiter and figure out in linear temporal logic that, okay, you can't have a deadlock and the system works all the time, basically. Ontology building is, how do you do that? So here's a natural language sentence. When the flying engine activates, the propeller shall be cancelled until the ignition starts. And you can basically analyze all the different parts here. Oh, there's a font error, so not everything points at the right thing, but it worked. And you can, from that, you can do natural language processing and extract things, depending on how that is. Let me, I'm a little bit late, but I can give you this presentation. Where does that leave us overall? So there's a vision of this integrated process and tool landscape. The reality is pretty far away still. Quite a few good things, I think, can be done. You can use these tools, like from Ria's company, to write high-quality requirements. And no matter what way you use to get to formalized requirements, whether you do that manually or use something more automated, you're already a big step forward when the natural language is actually high quality and has been checked for consistency, is based on an ontology. We can use Modelica to make requirements executable. At the moment, everything we have done has never used this automated process from a natural language. We rebuilt the natural language requirements in Modelica, but we still gain a lot from that because it automates the design process a lot. And so there are really initial ideas of doing this transformation from natural language into something formal for formal or simulation-based verification. But there are still many missing links and open questions I see.